All right, so let's look at our second. Let's look at our second integration technique today. You guys have done partial fractions before, right?
Yeah.
That word should not be completely foreign. One of the main reasons you did it is for these kind of decompositions. So, just like last time, I said partial fraction decomposition in calculus is just another way to change an integral you can't do into one or more, usually more, that you can do. That's the same thing that we did last week, right? Like when you do integration by parts, you're using some kind of substitution algorithm, which we showed where that came from, and then pumping this guy out, right? So that this part's done, and then this is hopefully an integral that you can do, or you can repeat or do a wraparound or something. But see, it's the same idea, it's just different methods, okay? So partial fractions is another way to approach that beast. Partial fractions is called for when you have very complex rational functions. So if you see very complex rational functions, that doesn't mean automatically try partial fractions, but your mind should be thinking, yeah, if I can't just do a u sub, it's probably that, okay? This is not too complex of a rational function, but that's just because we want to start with something easy, okay? So, can you guys help me decompose this by partial fractions? The integral part's easy. Something with A, B, and C. That's good. I like it. We remember some. Okay, so how do we set this up? First, don't we try to like factor? Is that what Paul's saying? Okay, so is this one factor?
No, x minus 6, x plus 1.
And oh yeah, if it doesn't factor, you can still do partial fractions. So we'll do one of those either today or tomorrow. Like if you have to use the, what else would you have to do if it didn't factor? Quadratic formula. You can still apply this technique. I'll show you how. Okay, it's just a pain, but I've had to do that before in advanced math. So
I factored it wrong. It's x minus 3, x minus 2.
yeah, this doesn't give us positive 6. Oh. You caught it. Good job. All right. There we go. So these are linear factors. Today we're just going to do linear factors. Tomorrow we'll do repeat other kinds of factors. These are both linear terms. So the form we set up is we just forget about the integral for a second, and we say we know by partial fractions that that complex fraction can be broken up as a sum of two fractions like this, where A and B are unknown and we have to figure those out. So there's several ways to figure those out. You can kind of guess some convenient numbers to figure them out. You can also do what's called equate coefficients. Sometimes one way is a lot easier than another. Sometimes one way is the only way that will work. So we'll try to do a variety of problems, okay? This one is one where you have two really convenient values. First, you multiply through and make this equation solvable. How do I do that? You don't want fractions in an equation that you want to solve. Common denominator, right? It shouldn't be a big leap of faith for you guys to realize if I want to solve for A and B, I don't want yucky fractions. So I better use the common denominator, which is what?
X minus 2 times x minus 3.
So you can actually draw it in there. I'm not going to because it like gets really messy, you know what I mean? So multiply that through all three sides, this common denominator, and you get what? 1 equals, what happens here? The x minus 2 quantity cancels. You get the x minus 3 left. Are we good? And then on this one, you're going to have a b and the x minus 2 left. Any questions? So if you want to actually put this in a different color on all three of those to see your cancellation, do it. So now, here's an equation. It's the same thing. These are both equations we wanted to solve for A and B. All we need is A and B. What are some convenient values that'll make stuff go away? 3 and 2. So say let x equal 3. Because these have got to be true for all x's. So what we're doing is picking convenient x's that'll make it easy to see. That's going to make this part go away, right? 0. So we'd get 1 equals 0a. I'll even write it down. 0a plus b times what? 1. So that says 1 equals b. Ha! It was easy. Oftentimes it will not be so easy, especially since you're going to do a lot of problems, right? Okay. We use Brenna's other convenient choice. And like I said, sometimes there won't be enough convenient choices and you'll have to attack it another way. So we'll see that. Anyway, if I plug 2 in, nothing happens here. We get a times -1 and b times 0 gone, so that's a is -1. Okay? We good? So that means this guy is equivalent to the integral, what?
-1 over x minus 2 plus 1 over x minus 3.
You guys agree with Brenna? And then that's a sum of integrals, so we could distribute the integration, right? Maybe like this. How's that? And those are both integrals you should know. What can we do with a constant? That gets pulled out in front. And what's the integral of 1 over x?
X minus.
Does this have anything with a chain rule in it? So it's just the negative natural log of what? Of that thing. Now watch it. Most of the time there's going to be like some kind of little chain rule issue you got to watch on those. Okay, most of the time. This is an easy one. So then what? Plus the natural log of x minus 3 plus c. Done. Okay. Once again, took an integral we couldn't do with some kind of substitution, broke it into two ones that we could do. Okay, sometimes one of these ones that you have down here you'll have to do a u sub on or something. So let's do at least one more, maybe two more.
Do you think there would be, after we do partial fractions, where we have to do integration by parts on
Maybe at the end of our unit, but not now. I don't think they'll be in this section. It could happen, so be wary, but very. I mean, if they do that, it's probably like one or two problems like that. So I don't think they're going to hit you too much yet, but I'm not sure. Good question. Okay, how about this one? There's all kinds of variations on partial fractions. We're definitely going to need to do a lot of these problems. Lots of variations that can happen. So I'll show you most of them, but I might not show you all of them. You guys are going to have to figure a couple out yourself, I think. Okay. One of the first things you want to check as soon as you look at that and you're like, God, there's no substitution that's going to work. There's no way this is integration by parts. You know, it doesn't look anything like that. I'm going to use partial fractions. The first thing you want to look at is the top degree bigger than the bottom? If it is, you should use long division first, and you might not even need to use partial fractions. You know what I mean? You could change this using long division into something that you might be able to integrate, okay? So we'll see some problems like that too. This one is bigger on the bottom, right? So this is probably, I mean, there's no guarantee, but it's probably doable that way. So any suggestions? Leave the top alone. You can try to factor the top too. It looks like maybe it factors. Looks kind of nice, I bet it does. But does the bottom factor?
X.
Okay.
X plus 1.
What's Paul saying, guys? X plus 1. Oh, this is x plus 1 times x plus 1, isn't it? If we continue to factor, just checking. So we could write it like that then, right? Or we could write both x plus 1s. I'm going to write it like this and not take another step. But the main reason I'm going to write it like that is because I can see how many times does this factor happen? Twice. So here's what you do if you have a repeated linear factor, okay? Or a repeated any kind of factor, actually. So those are still both linear factors, so we're not going quadratic factors or anything yet. All right, so let's get away from the integration, do some scratch work. Maybe we'll finish the integration over here. Let's do our partial fractions over here. So we're going to say 5x squared plus 20x plus 6 over that equals what? What do you guys think?
A over X
It's a linear factor. It happened once. We don't need to do anything different. And then
Plus b over 1 plus x, or x plus 1 squared.
and there's a repeated linear factor, so now we gotta go like this. You guys see the modification to the algorithm there? So if there's a repeated factor, you kind of have to do it twice. The first time is to the 1 power, the second time is to the 2 power. If it's repeated 3 times, you'd have to do it 3 times. Okay? So now we multiply through by the common denominator, which is always really going to just be this thing, isn't it? So let me do that. Try to use a different color here. So I'm going to run out of space here. 5x squared plus 20x plus 6 on the left. And what's left here when we hit that with it? A and x plus 1 squared, Austin says. Good. Plus b, and what's left here when you hit that with this? The x is going to be left. And 1x plus 1. Good. Yep. And then this one, all of that part's going to be gone, but we'll have an x left. So there's the equation we have to solve. We need a, b, and c. So like I said, there's different ways to do that. Are there some convenient values that might work this time? Yeah, let's try to do it by convenient values again. Okay, so what would be a convenient value? You said 0, Brenna? So the left-hand side, what would we have? So we'd have 6, because those go away. And then 0 here would be 1 squared. You might sometimes just write this out. It depends how trustworthy you think you are. I would imagine you guys are pretty good by now, but you know what's best for you. 0 is going to make this term go away, and this term go away. Oh, that's easy. So a is what? 6. Nice. Someone else, Sam, what's another convenient value I could plug in and look at? -1. Very nice. So if we put -1 in, we're going to have to be a little more careful, right? So we get 5 minus 20 plus 6 equals, this goes away, and -c. You guys follow that? So what is that? 11 minus 20 is -9. So c is 9. Okay, do we have any other convenient values we could pick? Ah, Austin's saying, hey, you have A and C already, can't you find B? Sure. What value should we pick, though? We got to pick some value of x. This is supposed to work for all x values possible, right?
1.
It doesn't matter. Pick anything you want. It's supposed to satisfy all x values. That's not really convenient, but we just need anything now. It'll work. We got lucky, though. It doesn't always work that way. So I'll have to show you one maybe tomorrow where something bad happens. Well, not bad. We just have to do more. Anyway, so if we plug in 1, what do we get? 5, 25, 31. See, I like to keep track of these with bullet points in my work. I'd definitely be neat. Neatness will be an issue on this assignment, so try to be neat. And then what 1 goes in there, we get A times how much? 2 or 4? 4. Don't forget, there's squareds and stuff in here. Watch out for those. And then we have what? 2b plus c. But we know that c is 9 from right here, and a is 6 from right there. So it's 31 equals 24 plus 2b plus 9, and of course we can get b. I'm going to see if I can do it in my head. Let's see. 31 minus, is this what? I can't do it in my head. Jeez. 33. So that's -2.
So b equals -1.
Yes. Gosh dang it.
Okay, in the pharmacy department, on this carousel thing, I have to count out the original count they have on there when I'm restocking, and I've had to recount so many things because my mental math is crappy.
My mental math is not always the best either. I'm always focused on the teaching and it takes me effort to do mental math. Okay, so we've got how many pieces? 3 pieces. So this integral is equal, we can put it over there or over here, equal to 6 over x plus what? Oh, is it minus? Minus 1 over x plus 1, and then what? Plus, sorry, timer. Guess you guys got done in time. Plus 9 over x plus 1 squared. Distribute the integral. I'm not going to show that step. You guys want to try those out? See if you can get those integrals. Good practice, and we'll see if you match me. Have them? You guys match me? This is the one that always gets everybody, right? Make sure you're comfy on that one. Remember, you can do like u if you want. It's really just like u to the negative 2, but you add 1 and divide by negative 1, so that's really just negative 1 over u. Okay? I don't know why that gets equal. It is a little tougher, I guess. Okay, I think we'll be done for today. We'll pick up. Oh, maybe one more thing. One more little suggestion. You might need this. Start working on it. Whoa. Let's think about another simple one, and let's maybe not do it all, but the book had like this one, for instance. What if you had this? That one looks pretty simple, right? What's the difference?
Doesn't factor.
It doesn't factor, so are you out of the... Like, how do you do this problem? There's no other integration technique to do this problem I'm not aware of, unless it's in the tables, which is, you got in the tables by doing it this way. You just give up? Use the quadratic formula. Let's just set it up and then we'll stop there. So if we use quadratic formula, how's that go? Negative b, so 5 plus or minus...
Square root of b squared minus 4ac.
Okay, there's b squared minus 4ac, 2a, what do we get? Let's whittle this down. It's 25 minus 20 is 5 over 2. Okay, can you express this in factored form now? You betcha. It just looks weird, it's not hard. How would this go? X
Minus 5 plus root 5 over 2.
and if we go minus, then that takes care of that, right? Because this is the actual 0. If you go x minus the 0, that gives you the factor, right? Does that make sense? And then you'd have x minus 5 minus root 5 over 2. Could we then use those and go a over that and b over that? Yeah. Finding some of the convenient values or whatever, it might turn into a little bit messy algebra, but it'll definitely work. Okay? So don't let that freak you out. It's not that big. It was actually not that bad. You'd take care of it in a minute or two. All right, we'll do some more non-linear examples tomorrow, is what we said, I think.